We talked about diagnostic tests, and we covered autocorrelation, we covered heteroscedasticity, and specification errors. Today, we'll start our first lecture on time series econometrics. We'll cover dynamic models and stationarity. We'll learn what that means and why that is important for time series data and time series regression. Just as a quick recap of the last lecture, we talked about heteroscedasticity. What is heteroscedasticity? What is the problem when we have heteroscedasticity? What are the consequences for OLS estimation when we have heteroscedasticity? How to deal with heteroscedasticity? Do you remember what is heteroscedasticity? Can you now say heteroscedasticity? Well, it took me time to get used to it. Okay, I'm not asking you to repeat it, it's fine. You're trying, I see like people trying to say it. So heteroscedasticity happens, or heteroscedastic error means that you don't have, the error term doesn't have constant variance. And this is the assumption number 4. We made, in our model, you remember the first lecture, we made 7 assumptions, and we said since these are assumptions, we need really to test whether they are true or not. So one of which was assumption 4 about heteroscedasticity, about the variance of the error term, and what we'd like to see is a homoscedastic or equal variance error term. That's when we give it this notation sigma square, so it's constant variance. But this is unlikely the case with cross-section data, and we explain why it is unlikely with cross-section, but in all cases you need to test for that formally. But in cross-section data, usually it depends on I, so that means it's not constant. Then we explained that, okay, with OLS estimation, OLS remain unbiased, consistent, which are good properties that we want. These are desirable properties for our estimator, but less efficient, so they're no longer blue. Okay, it's not the best anymore. Okay, and that is the problem. And obviously, that put the standard errors into question, and any inference based on that is questionable as well, because we can't trust the standard errors. One way to detect for heteroscedasticity is to plot the residuals, or you could apply the Bruch-Began test or White test, and both follow the same, has the same null hypothesis, homoscedastic error term. So if you have a small p-value, you reject small. When I say small here, I compare with a significance level. Let's say 5% or 1%. So if you have a small p-value, that means you reject the null hypothesis. That means your errors are not homoscedastic, they are heteroscedastic. And then we explain how we could, if we apply the heteroscedasticity consistent standard errors, that will correct the standard errors. So the estimated coefficients remain the same, but what has changed, if you remember from the example we gave last time, was the standard errors mainly. So we've got the same coefficient but different standard error, which were corrected for taking into account heteroscedasticity. Then we move to autocorrelation. We discuss again, this was assumption number 5 we made. The covariance between UI and UJ, so any 2 errors should be 0, and this is unlikely with time series data. So when you deal with time series data, so you should expect autocorrelation or your errors to be serially correlated. And again, similarly here we have unbiased estimator, consistent estimator, but no longer the efficient one or the best one. You still can plot your residuals the same way to see if there is any pattern, and if that's the case, then you should suspect the presence of autocorrelation. And you could use Durbin-Watson test, and we explain what assumptions, the assumptions under which you can apply Durbin-Watson test, and or Bruch-Began, Bruch-Godfrey LM test. And how to correct for that? This is what we did last time. We applied this procedure, the heteroscedasticity autocorrelation consistent standard errors. Okay, HAC, that's for short. So HAC, that's what we did in the lecture. But also we said we could introduce lags, and this is something we will do today. Okay, we'll show you how we can introduce lag into the model. That includes time series data. And then finally we move to specification errors. And when we talk about specification errors, again, the assumption number 7, A7 we made, is that the model is correctly specified. And when we talk about the specification of the model, we talk about many things, but before we jump into explaining what that is, we explain that there is no such perfect model. So always you need to compare between different specification and see which one that sounds the best one or the correct one, but there's no such perfect model anyway. But anyway, so the cases we discussed, when we have underfitted model where you for some reason dropped important variables, and the effect of these important variables will cause this issue of omitted variable bias, and we explain that the issue here is very serious because the estimation or the estimator will be biased. Do you remember when we give the example about family income, and we said if family income depends on husband education and wife education and number of kids less than 6 years old, and then for some reason we drop 2 of the variables and we just run a regression of family income on husband education, okay, and we show that the coefficients are different, and that you overestimate the effect of the house of the husband education on family income because you omitted the other 2 important variables, okay, which we assume that they are important. But anyway, so that also in the other case, the overfitted models, when you include irrelevant variables into the model. So some variables, for some reasons, some people think when they have higher R squares, so that's a better model. That's why they think, okay, if I add 1 or 2 more variables that improve or increase the value of R squared, so that might be better. In the same time that these variables are not actually relevant. And we did some exercise last time. We included in our model 2 variables that they just created independently. They are not actually related to family income at all. And we saw that this was how this would affect the estimation. And also, this includes the incorrect functional form. We discuss the case, what we mean by linearity. You remember in lecture 2. So we didn't cover it last lecture, but we covered this in lecture 2, and we talked about your model could be linear in as long as it is linear in parameter, you still can use OLS, but the functional form can be different, or it doesn't necessarily have to be linear in variables. So the variables could be nonlinear. So whatever that is, so that means you need to make sure that you're following the correct functional form, and one really good way to do this is just to plot your dependent variable and see maybe if there's any pattern can tell you the right or the something about the functional form. Measurement errors, we explain what would happen if the measurement errors in y in the dependent variable, and what would happen if the measurement errors happen in